40 million acres of American farmland run on synthetic nitrogen every single year. In 2023, American farmers applied over 12 million tons of it. The cost runs into billions of dollars annually. Billions. And every spring, the cycle resets. The truck comes. The tanks fill. The invoices stack. And the soil, the actual living ground beneath every boot and tractor tire, grows a little more dependent, a little more hollow, a little more unable to feed itself. Hi viewers, here is a simple question that will take you 5 seconds to answer. Drop a number in the comments right now. How much do you spend on fertilizer each season? Or if you are not a farmer, just type 0. Let's see the range. Darnell sets the bill down. He walks out to the back field, the one his grandfather called the quiet field. The grass there is a different shade of green. Darker. Thicker. Nobody sprayed that corner. Nobody bought anything for it. It just grows. He crouches. Pulls a handful of soil. It is dark, almost black, loose between his fingers. It smells like rain that already happened. Something lives in this dirt that does not live in the rest of the field. He does not know what it is yet. But 12 miles away, in the county agricultural library, a folder sits inside a 1947 filing cabinet. Inside that folder is a photocopied bulletin from a land-grant college. The title is handwritten in faded pencil at the top. Someone underlined a single sentence twice, hard enough to score the paper. That sentence describes a plant. A plant that makes fertilizer. Continuously. Without a factory. Without a purchase order. Without a bill arriving on a Tuesday morning to ruin a man's coffee. The number that should not exist, 50 to 200 pounds of nitrogen per acre per year, from a single living plant, is sitting in a dusty folder inside a library that closes at 5. And Darnell Okafor has no idea it is there. Before factories learned to fix nitrogen, farmers already had. The soil is darker here. That is the first thing the farmhands notice in the winter of 1734, standing at the edge of Charles Townsend's field in Norfolk, England. They do not say anything clever about it. They just notice. The ground is darker where the clover grew last season. The wheat that follows grows thicker. Taller. The stalks do not lean. They stand. Townsend himself walks the rows in the early morning, boots sinking into English mud, and he counts the heads of grain. He is not a romantic. He is a man who measures. And the measurement is undeniable. Fields that rested under clover yield more than fields that did not. Every time. Without exception. He calls it rotation. 4 fields. Wheat. Turnips. Barley. Clover. Then back to wheat. The cycle repeats. The soil does not deplete. The yields do not fall. By the 1740s, the idea had spread across British farms like a slow fire. Landlords resist at first because the model requires patience. 1 full season given to a plant you do not sell. 1 full season of what accountants call lost revenue. But the farmers who follow the rotation do not care what the accountants say. Their wheat speaks for itself. By the early 1800s, the model crossed the Atlantic. Kwame Delacroix, a free black farmer in central Virginia, learns the rotation from a neighboring farmer who learned it from a pamphlet printed in Philadelphia. Kwame has 12 acres, 3 of which are nearly exhausted from years of tobacco. He plants red clover on those 3 acres in the spring of 1811. He does not harvest it. He turns it under in late summer. The following spring, he plants corn. The yield on those 3 acres doubles. He writes this down. 1 sentence in a leather journal his daughter will later donate to a county historical society, where it will sit unread for 140 years. Agricultural bulletins from American land-grant colleges in the mid-1800s document the same pattern across dozens of case studies. Legume rotation increases measurable soil nitrogen. Subsequent grain crops show yield improvements ranging from 30 to 60%. The data is clean. The method is simple. The cost is a bag of seed. Farmers observe the results, but most of them cannot explain the mechanism. The soil simply improves. The darker the ground after clover, the better the next crop grows. They do not yet understand what lives inside the roots. They do not know about the bacteria. They do not know about the nodules or the pink color inside those nodules, which means something extraordinary is happening underground. They only know what they see. Dark soil. Thick wheat. Full harvests. And for over a century, that is enough. Then chemistry entered the field, and biology was no longer required. The explosion comes first. That is the part most people never hear. Before the fertilizer bags, before the farm trucks, before the spring application schedules, there is a world war. There are munitions plants. There are factories built at emergency speed across the American Midwest and South, designed to convert atmospheric nitrogen into explosives at a scale the world had never attempted. The process has a name. Haber-Bosch. Two German chemists, Fritz Haber and Karl Bosch, cracked the problem in 1909. Nitrogen gas, which makes up 78% of the air but cannot be used directly by plants or humans, is forced into ammonia under extreme heat and extreme pressure. It is one of the most consequential chemical reactions ever industrialized. It feeds armies. It builds bombs. It changed the 20th century. Then the war ends. The factories do not close. They pivot. Munitions infrastructure converts to fertilizer production. The same process. The same pressure. The same heat. But now the output goes into bags instead of shells, onto farms instead of battlefields. And the timing is perfect for an industry looking for a new customer. Tomas Whitfield, an agricultural extension officer in rural Tennessee, drives his government truck from farm to farm in the spring of 1948. In the back of that truck are sample bags of synthetic nitrogen fertilizer, free of charge, provided by a manufacturer looking to establish a market. Tomas is a good man. He believes what he is told. The product works fast. Visibly fast. He watches corn respond to synthetic nitrogen within 2 weeks of application, and the transformation is immediate. He stops recommending clover rotation. Not because someone tells him to stop. No memo arrives. No directive comes down from Washington. He stops because the new product is faster, easier to explain, and fits the machinery that farms are rapidly acquiring. Tractors do not wait for biology. Planters run on schedules. And synthetic nitrogen fits the schedule perfectly. Across the country, the same shift happens farm by farm, county by county, extension office by extension office. The recommendations change. The seed catalogs thin out. Clover acreage drops. The logic is not hidden. It is simple. A market that rewards products you must purchase every single year will always find a way to make annual purchasing feel necessary. Synthetic nitrogen requires a truck, a supplier, a transaction, and a repeat order next spring. Clover requires a bag of seed, a season of patience, and nothing else. One fits on a ledger. The other does not. Factories scale. Biology waits. And what cannot be invis slowly disappears from the curriculum. But the chemistry inside the soil never stopped working. Cut the root open. That is what Zora Mensa does on a cold March morning in her research greenhouse at a land-grant university in Ohio. She pulls a clover plant from the soil tray, shakes the dirt free, and holds the root under the fluorescent light. Along the root system, clustered like small pale grapes, are nodules. Dozens of them. She takes a scalpel and slices one open. It is pink inside. That color is not decoration. That color is evidence. It means the nodule is active. It means a transaction is happening underground that no factory on Earth fully replicates. Zora sets the plant down and writes one word in her field notebook: working. Here is what is happening inside that nodule, broken down to its exact sequence. Clover roots release chemical signals into the surrounding soil. Specific signals, aimed at specific bacteria. The bacteria, a genus called Rhizobium, detect those signals and move toward the root hairs. They enter. The root responds by forming a structure around them. A nodule. A sealed chamber. A controlled environment where something that should be impossible becomes routine. Atmospheric nitrogen makes up 78% of every breath taken on this planet. It is everywhere. It is free. And it is completely unusable by plants in its natural form. The nitrogen molecule holds itself together with a triple bond so strong that breaking it requires either extreme industrial force or a very specific enzyme. The enzyme is called nitrogenase. Rhizobium produces it. Inside the nodule, nitrogenase breaks atmospheric nitrogen apart and converts it into ammonia, a form plants can actually absorb and use to grow. This process is called biological nitrogen fixation, and it is one of the most elegant chemical partnerships in all of nature. But nitrogenase has one critical weakness. Oxygen destroys it. Clover solves this problem with a molecule called leg hemoglobin. It regulates oxygen levels inside the nodule, keeping them low enough to protect the enzyme but high enough to keep the bacteria alive. Leg hemoglobin is the reason the nodule is pink. It functions similarly to hemoglobin in human blood. A plant producing what amounts to a biological oxygen manager inside its own root system, all to protect a bacterium that feeds the soil for free. The measured output of this partnership is not trivial. White clover fixes between 80 and 130 pounds of nitrogen per acre per year under normal field conditions. Red clover reaches 150 to 200 pounds per acre under optimal conditions. These are not projections. These are figures confirmed through replicated field studies at universities across the United States. And the benefits do not stop at nitrogen. Soil microbial diversity increases around legume root systems. Soil aggregation improves, meaning water moves through more efficiently and roots penetrate more easily. Nitrate leaching, the process by which synthetic nitrogen washes out of the soil and into waterways, drops significantly in fields managed with clover rotation. When clover dies or gets incorporated into the soil, all that fixed nitrogen becomes plant available for whatever crop follows. Gradually. Steadily. Without the volatilization spike that causes synthetic nitrogen to peak on day one and decline from that moment forward. Zora closes her notebook. The nodule sits open on the tray, still pink under the light. She has run this experiment 41 times. It works every single time. If this works in theory, does it work in real soil today? Darius Calloway does not trust numbers that he did not measure himself. He is standing in his Pennsylvania field at 7 in the morning, holding a soil sample in a clear plastic tube, watching the color develop in the testing solution. The field behind him is 5 acres. It has grown soybeans, then corn, then nothing useful for the past 3 years. The soil is tired. He can see it in the color, pale, almost gray at the surface, and feel it in the way it crusts after rain instead of absorbing. The test result reads 18 parts per million available nitrogen. He writes it down. Date, time, field quadrant result. He has a notebook for this. 3 columns, no exceptions. That same afternoon, he broadcasts crimson clover seed across all 5 acres. 1 pound per 1,000 square feet. He rakes it lightly, no deeper than a 1/4 inch. He does not add fertilizer. His neighbor tells him he is wasting his time. Darius writes that down too. The clover germinates in 9 days. Through the fall and into the early spring, it grows low and dense, a dark green mat across the tired gray field. Darius walks it twice a week. He crouches. He checks. In late February, he pulls a plant, shakes the roots clean, and examines the nodule clusters with a hand lens. They are there, clustered along every major route. He takes his pocket knife and cuts one open. It is pink. He stands up straight, exhales, writes one word in his notebook: active. 8 weeks after incorporating the clover into the soil, turning it under with a simple pass of the tractor, Darius pulls new soil samples from the same quadrants he tested in the fall. Same tube. Same solution. Same light. The result reads 47 parts per million. He checks it twice. 47. That is not a small shift. That is a 29-point increase in plant available nitrogen without a single purchased input. No truck came. No invoice arrived. No tank was filled. A plant did this. A plant and the bacteria living inside its roots, converting air into food, free of charge, while Darius watched football on Sunday afternoons. The corn he plants that spring on those 5 acres yields 38% more than the corn on the adjacent control rows that received no cover crop. He weighs every harvest load on calibrated digital scales and records the difference down to the pound. The data does not care about its neighbor's opinion. But Darius is honest about what he knows and what he does not. The result depends on factors he cannot always control. Soil pH has to sit between 6.0 and 7.0 for rhizobium to function properly. The soil needs adequate moisture during establishment. In compacted or chemically sterilized soils, nodule formation drops sharply, and nitrogen fixation slows to near nothing. This is not a miracle. It is a biological system with real requirements. But when those requirements are met, and they are not difficult to meet, the data lands the same way every time. Dark soil. Active nodules. Measurable nitrogen. Stronger yield. Darius closes his notebook. He looks across the field. The corn stands thick and green in the August heat, roots running deep into soil that fed itself. He thinks about the bill his cousin Darnell showed him last spring. $4,700 for 1 season of synthetic nitrogen. He thinks about what he spent. $14 for seed. So why isn't every field planted this way? The extension office smells like old coffee and government paper. Celestine Drummond has worked here for 19 years. She knows every farmer in the county by first name, knows which ones call before planting and which ones just show up with a problem already 3 weeks deep. She is good at her job. She believes in her job. And for 19 years, she has handed out the same nitrogen recommendation sheet, printed on pale yellow paper, updated every 5 years with minor adjustments, but never a fundamental change. She finds the clover bulletin by accident. It is tucked inside a manila folder misfiled under soil pH correction, dated 1952. She reads it standing at the filing cabinet, one hand still on the drawer. The data inside describes nitrogen accumulation rates from legume cover crops that match almost exactly what Darius Calloway showed her 3 weeks ago from his own field notebook. She sits down. She thinks about how many farmers she has sent to the fertilizer supplier over the past 2 decades. How many recommendation sheets? How many pale yellow pages? Nobody told Celestine to stop recommending clover. Nobody called her. Nobody sent a memo with instructions to push synthetic nitrogen over biological alternatives. What happened was quieter than that, and in many ways harder to fight. The training she received came from a curriculum developed by institutions that partnered with agricultural input manufacturers. The field days she attended were sponsored by companies that sold products by the ton. The yield data she was given to share with farmers was collected from trials that used synthetic nitrogen as the baseline, meaning every comparison started from a foundation that assumed purchasing was necessary. The system did not suppress biology. It simply stopped teaching it. Monoculture farming demands predictability. A corn farmer running 2,000 acres cannot wait for biology to cycle at its own pace. He needs nitrogen available on Tuesday because planting starts on Wednesday. Synthetic nitrogen fits that timeline. Clover rotation requires a full season out of production, or a carefully timed cover crop strategy that demands knowledge most extension curricula stopped covering 40 years ago. Timing is everything in agriculture. And biological systems run on nature's clock, not the market's. Celestine pulls out the pale yellow recommendation sheet. She looks at it for a long time. She does not throw it away. But she opens a new document on her computer and begins typing something she has not written in 19 years of government service. A case for clover. Because here is the thing that keeps pressing against the back of her mind like a splinter she cannot reach. The farmers who are struggling most right now are the ones most locked into annual input purchasing. The ones with the most debt. The ones most exposed when fertilizer prices spike, and fertilizer prices always spike eventually. The ones who have, without realizing it, traded long-term soil health for short-term yield predictability. Clover does not invoice you. Factories do. And institutions teach what scales, not always what sustains. Celestine saves the document. She looks out her office window at the county fields stretching flat and pale under the February sky. But what happens if you reverse the trajectory? Darnell Okafor is on his knees in the dirt before sunrise. Not praying. Testing. He pushes a soil probe into the ground at the edge of the quiet field, his grandfather's field, and pulls a clean core sample. The soil is dark and loose and smells like something alive. He already knows what the test will show. He has done this 4 times in the past 18 months. The numbers keep moving in the same direction. Up. He is not guessing anymore. He is following a system. And this is exactly how that system works, broken down to the specific steps that changed his farm. The materials are not expensive. White clover seed or red clover seed, available at any farm supply store, runs between $8 and $14 for enough to cover 1,000 square feet. For larger acreage, bulk pricing drops the cost further. 1 to 2 pounds of seed per 1,000 square feet is the target rate. Darnell also purchases a rhizobium inoculant specific to clover, a small packet of live bacteria that costs less than $5. Because his soil had been under synthetic nitrogen management for so long that native rhizobium populations were nearly gone. The inoculant restores the partnership that the soil lost. Step 1 is the soil pH test. This is non-negotiable. Rhizobium bacteria cannot function in highly acidic or highly alkaline soil. The target range is 6.0 to 7.0 on the pH scale. If the soil tests below that range, a lime application corrects it before seeding. If the pH is wrong, the nodules will not form correctly, and the nitrogen fixation rate collapses. Darnell tests every quadrant separately because pH varies across a field more than most people expect. Step 2 is broadcasting the seed. Early spring or late summer are the optimal windows, depending on the intended use. Darnell uses late summer for his cover crop rotation, which lets the clover establish before the first frost and overwinter as a low mat that resumes growth aggressively in early spring. He broadcasts by hand on smaller plots, and uses a walk-behind spreader on larger sections. The seed goes on top of loosened soil, not buried. Light raking, 1 pass, no pressure, ensures contact with the soil surface. No deeper than 1/4 inch. Deeper planting reduces germination rates sharply. Step 3 is moisture management for the first 10 days. Clover seed needs consistent light moisture at the surface to germinate. Not soaked ground. Not dry crust. Just damp. Darnell sets a reminder on his phone to check soil moisture every morning for the first week. Germination appears between 7 and 10 days under normal conditions. Here is the rule most people break. Do not apply nitrogen fertilizer during establishment. This is the critical error that kills the entire system before it starts. When nitrogen is already abundant in the soil, clover has no reason to partner with rhizobium. The plant reads the chemical signals in the soil, detects adequate nitrogen, and suppresses nodule formation entirely. The result is a clover plant that grows green and looks healthy, but fixes nothing. It is a passenger, not a producer. The whole point of the system disappears. Let it build its own. Once the clover is established and growing, Darnell mows it before full bloom, not after. Pre-bloom mowing keeps the plant in a vegetative state, which maximizes biomass production and nitrogen content in the tissue. The clippings stay on the surface. They do not get bagged or removed. They break down where they fall, releasing nitrogen back into the top layer of soil and feeding the microbial community that makes the whole system function. When the cover crop cycle ends, the clover gets incorporated, turned under or crimped flat, and given 6 to 8 weeks to decompose before the next cash crop goes in. That window is where the nitrogen transfer happens. The decomposing plant tissue releases fixed nitrogen gradually into the soil profile exactly when the following crop's root system is developing and ready to absorb it. Year 1 results are modest. Nitrogen accumulation begins, but soil organic matter has not yet shifted significantly. In Year 2, the change becomes visible without a test. The soil color deepens. Water infiltration improves. The ground stops crusting after rain. Year 3 and beyond, the nitrogen cycling stabilizes, and external input requirements drop in a measurable, documented way. Darnell pulls the soil probe core out and holds it up in the early light. Dark. Dense. Alive. $14 of seed 18 months ago. The soil will not look dramatic at first, but wait. The curve is the thing nobody talks about. Synthetic nitrogen has a performance curve that peaks on the day of application. From that moment, it begins to decline. It volatilizes into the air. It leaches through the soil profile into groundwater. It gets locked into forms that plants cannot access. The farmer who applies it on Monday gets the strongest response by the following week. By midsummer, a significant portion of what was purchased has already left the field in one form or another. The yield response is real. The investment is real. And the depletion that follows is also real. Clover's curve runs in the opposite direction. Aminata Osei figures this out in her second year of cover crop rotation on her family's Georgia vegetable operation. She is not an agronomist. She is a farmer who keeps records, and her records show something that takes her 3 readings to fully accept. The soil on her clover-rotated beds is not just holding nitrogen better than her conventionally managed beds. It is building something underneath that she cannot see but can measure. Soil organic matter. This is the number that changes everything long-term. Soil organic matter is the accumulated residue of decomposed plant and microbial life, and it functions as a slow-release nutrient bank, a water retention system, and a structural framework for root growth all at once. Aminata's organic matter percentage in her rotated beds moves from 1.4% in Year 1 to 2.1% in Year 3. That shift sounds small. It is not. Each 1% increase in soil organic matter allows an acre of soil to hold an additional 20,000 gallons of water. In a drought year, that number is not academic. It is the difference between a crop and a loss. Fungal networks expand in soils managed with biological inputs. The mycorrhizal fungi that connect plant root systems underground, extending their effective reach by hundreds of times, thrive in environments rich with organic matter and low in synthetic chemical disruption. These networks transfer nutrients between plants, signal stress responses, and stabilize soil aggregates in ways that no purchased input replicates. They build slowly. They compound over time. And they collapse quickly under heavy synthetic nitrogen application, which is why degraded soils become more dependent on external inputs the longer they are managed that way. The comparison comes down to two curves drawn on the same graph. One line starts high and drops from the moment of purchase. The other line starts near zero and climbs, season by season, year by year, building something that does not wash away when it rains and does not evaporate when summer turns hot. Aminata stands at the edge of her best bed in the third year of rotation. The tomatoes there are darker green than anything in the adjacent rows. The soil under her boots gives slightly, the way good ground does. She does not need a test to know what is underneath. She has the tests. She has the numbers. She has 3 years of harvest records that tell the same story in pounds and dollars. Synthetic peaks on day 1. Clover begins at 0. Then it rises. And that reversal changes more than yield. The price alert hits Darnell's phone at 6:42 in the morning. Nitrogen fertilizer futures are up 18%. Third spike this year. He sets the phone face down on the kitchen table. His cousin Darius is sitting across from him, both hands wrapped around a coffee mug, reading the same notification on his own screen. Neither of them says anything for a moment. The kitchen is quiet. Outside, the early field is still gray in the pre-dawn light, but both men know what is under the surface of that ground now. They have tested it. They have measured it. They have watched the curve move in a direction that does not depend on a futures market. The atmosphere above every farm in America is 78% nitrogen. It has always been there. It is there right now, above every struggling farm, above every farmer opening a price alert at 6 in the morning and doing math that does not add up. Free nitrogen, suspended in the air, is completely inaccessible without either an industrial factory running at extreme heat and pressure, or a living plant and the bacteria inside its roots doing the same conversion for the cost of a seed. Soil degradation in the United States is not a future problem. It is a current one. The USDA has documented measurable topsoil loss across major agricultural regions for decades. Topsoil that took centuries to build the roads in a single generation of extractive farming. Soil that cannot hold water becomes vulnerable to drought in a way that no irrigation system fully compensates for. And soil stripped of its microbial community cannot respond to biological inputs even when farmers try to restore them, because the infrastructure that makes those inputs work is already gone. Darnell thinks about his grandfather's tin box under the floorboard. 26 years of farm receipts. No nitrogen line item. Not once. He is not against factories. He is not against synthetic inputs used carefully in specific circumstances. That is not the argument, and it never was. The argument is simpler. A system that requires annual purchasing to maintain basic soil function is a system built on perpetual dependency. And dependency at scale is a vulnerability that shows up in a price alert on a Tuesday morning, whether a farmer is ready for it or not. The atmosphere is 78% nitrogen. You already own it. You just have to unlock it. Darnell picks up his phone. He does not check the price alert again. He opens his soil test app and logs the morning sample from the quiet field. The number that appears is not a bill. It is a balance. So the final question is not scientific. The last entry in Ezekiel Okafor's receipt tin is dated March 1987. Darnell finds it on a Sunday afternoon, sitting on the kitchen floor with the tin open in his lap, going through every receipt the way he has done a dozen times before. But this time, he is not looking for the nitrogen line item he already knows is not there. He is looking at everything else. Seed purchases, cover crop mixes, soil amendment costs that run so low they barely register, and harvest yields recorded in a separate ledger in his grandfather's careful handwriting, season after season, that do not decline. They hold. Some years they climb. Ezekiel Okafor farmed the same ground for 31 years without depleting it. That is not a miracle. That is biology managed with patience. Synthetic fertilizer sells nitrogen. Clover manufactures it. One process requires fossil fuel combustion, high-pressure reactors, national distribution networks, and an invoice that resets every spring. The other requires sunlight, atmospheric gas, a bacterium that has lived in soil for millions of years, and a plant whose seed fits in the palm of one hand. The Haber-Bosch process is extraordinary. It feeds billions of people, and that fact deserves acknowledgement without qualification. But the existence of one system does not erase the value of the other. What the past 80 years have demonstrated is what happens when one system becomes the only system, when biological nitrogen fixation disappears from agricultural education, from extension recommendations, from the practical knowledge passed between generations of farmers. The soil remembers what was lost even when the farmers do not. Zora mensa's pink nodule is active under a fluorescent lab light. Darius Calloway's 47 parts per million, measured twice before he believed it. Aminata Osei's organic matter is climbing year after year on a Georgia vegetable farm. Celestine Drummond's new document, replacing 19 years of pale yellow pages. Darnell Okafor's quiet field, darker than everything around it, fed by nothing purchased and nothing borrowed. These are not isolated stories. They are data points on a curve that runs in one direction when biology is allowed to work. The economics that displaced clover were not a conspiracy. They were logical. A market logic that rewarded scale, speed, and annual transaction over patience, biology, and compounding return. That logic still operates. It operates every time a price alert hits a phone at 6:42 in the morning. Every time a farmer signs a purchase order for what the atmosphere already provides at no cost. The nitrogen is already in the air in every field in this country. 50 to 200 pounds of it, per acre, per year, available through a partnership between a plant and a bacteria that costs $14 to establish and improves from that moment forward. The question was never whether it works. Darnell closes the tin box. He sets it on the kitchen table next to his cold coffee, his soil test records, and his grandfather's harvest ledger. He looks out the window at the quiet field. It is green this morning. Dense and low and working, even now, even without him watching. The trajectory reversal does not require a policy change, a government program, or an industry shift. It requires a decision made by one farmer, on one field, in one season. You can manufacture fertility. Or you can grow it. The nitrogen is already in the air. Will you pay for it, or partner with it? If this story made you think differently about the ground beneath your feet, share it with someone who needs to hear it. Drop your thoughts in the comments below. Your perspective might be exactly what another farmer or gardener needs to read today. And if you are not subscribed yet, subscribe now and turn on notifications. Because the next story on this channel is one you will not want to miss. It goes even deeper into what industrial agriculture buried, and what a new generation of farmers is quietly bringing back. The ground is ready. The biology is waiting. And the next chapter starts the moment you decide to show up for it.